just a little bit of context on the project that we're doing. So my team tends to work on smart buildings, primarily on real-world applications and real-world test studies. So I'm going to be going through a presentation on a project that we've actually been doing for a hospital in Western Canada, and how we're trying to actually use symbolic regression to go kind of back to basics and understand how the hospital's behaving so that we can actually make a more robust conditioning or cooling optimization strategy. So really quickly, you can all read the agenda, standard approach for a conference. But let's start by establishing the research context. So we know that you need to have HVAC systems for comfort, especially in Canada, where we will typically in a given year go as far down as -20, -30 Celsius, and then as far up as +30, +40 Celsius. So we have quite a range that we're trying to actually work with. So our HVAC systems are doing a lot of work. On one of the other sides is we're really trying to get a sense if we want to be optimizing energy prediction and energy performance, we need to be able to predict how the systems are going to behave. So we've done a lot of work on how to infer cooling loads in buildings so we can actually be able to then turn around and develop sequences to be able to control that. Conventionally, you wind up using a lot of either black boxes, which you can trust on the data that you train them with, or white boxes that I personally find very complicated. If you've ever tried to do an RC model with all of the resistances and the capacitances and stuff like that, it gets very overwhelming. It's big for one room. It's ridiculous for a 500-bed hospital, right? Or a multi-building hospital campus. And the last problem that we're really trying to deal with is cold start. So the cold start is when you go into a new building, you want to do a data-driven or a partially data-driven solution, and you need to collect enough data to make it worthwhile. So we wanted to create an efficient and interpretable model for cooling load prediction. So something that doesn't use a lot of features, something that you can train up very quickly, and something that's actually very robust. And we wanted something that was small enough and simple enough that we could actually deploy it on an edge device and actually have it running locally on the system, because this is a computer, it's a hospital building automation system that we don't have real-time access to. So we can get data dumps, but we can't just see how the real-time data, we can't control things in real time. So we have to have the ability to make advanced predictions and be able to see. We also wanted to validate, and we actually wanted to benchmark our performance against linear regression and XGBoost that tend to be used. So most of us are familiar by now in the conference with different kinds of machine learning models. So you've got the physics-based models, which are the very explicit representations. You've got deep learning, but that's very data hungry, computationally expensive, and resource intensive. And sometimes it can be overkill. We don't necessarily always need deep neural networks for every problem that we're solving. And there's also the overfitting problem, right? So I think a few conference papers already at EC3 have talked about the challenge of people using random forest and finding that they've immediately overfit the data, even though random forest is supposed to be a little bit better than that in the decision trees. So we're looking at symbolic regression as white box, not in the sense that it's purely based on the building physics, but that it has full transparency of what is actually being manipulated, right? So symbolic regression basically learns your mathematical expressions directly from the data. So in that sense, it is a gray box method because you're trying to actually learn what the equations are, but you have the full transparency. So it's not like a neural net where if you look at it, you can see all of the different weightings, but a human can't look at it and really interpret what's going on. Nice thing about it is the models are small, people can understand them, and they perform quite well. So here's our hospital. So this is the hospital that we're working is in Vancouver, Canada, so that's on our west coast. And it's an ASHRAE climate zone 4. So this is kind of a temperate, cool climate, a little bit more mild than Toronto, which is where I'm based. So winters -10, -15 degrees, summers +20, +25. So still non-trivial in terms of heating and cooling loads, but fairly significant. What we were trying to do is figure out how the building is actually performing, what the cooling loads actually were, and could we predict them. Back last year, we presented a paper on the cooling load optimization and looking at how these loads can be distributed. And actually in a couple of weeks, I'll be at ISARC presenting how we've actually done optimization using a black box model, using an emulator based on this symbolic regression for the chiller plant as well. The first step for us was to be able to figure out if we could actually predict the cooling loads. So if I look up here, we have the data that we're actually using. This is all standard building automation system data. So One of the rules in my group, for better or for worse, and Margin talked about this yesterday, is we don't make people install other sensors. So if something isn't a standard data point on a standard building automation system, we don't use it. The good thing about that is it means that we can go into pretty much any building and they'll all have the same points. The bad thing is that we often have to do a bit of extra work to really understand how to fit the data, right? But you have, your chilled water supply and return temperatures, your flow rate. You've got your weather station data. And then you have things like what day is it, what hour is it, et cetera. This cooling load that we have, we didn't put the formula down just because of the space, but it's a very simple, it's sensible cooling load. MCP delta T, right? So your loop temperature coming into the chiller minus coming out of the chiller times your volumetric flow rate times your mass times your coefficient of specific heat capacity of water. So it's very straightforward, and we're just looking to see what the load that the chiller actually sees is, because that feeds into our chiller optimization model. So we used PySR, which is just a symbolic regression package, and Julia, which was our programming backend. And we limited it to the 4 simple operators. So when you do symbolic regression, you can say you're allowed to use exponentials. You can use second, third degree exponentials. You can use square roots. You can use exponents. You can basically tell it which functions it's allowed to use. If I was doing a fan law, I'd be using a cubic because I know as a mechanical engineer that it's going to have that relationship. Our target was the cooling load, so that's what we were trying to calculate. And we used the features as we saw them. We were doing an L2 distance loss function to try and minimize the error that we actually had on our fits. So we were trying to be really aggressive. Like I said, one of the things we wanted to look at was to see how quickly we could retrain the model. We'd initially started working with a couple of months of data, but we decided to push it and see how short a training window we could use. So we created 3 models. One that was very complicated. You'll see the full equations on the next slide. So SRA was our most elaborate model, and that was given 5 days of data, the 8th to 12th of July. SRB was a much more simplified model, like very, very, very simple, you'll see it, on the same 5 days of data. And then SRC was a third model that we trained on 3 days of data, because we wanted to see if it was possible to get something that was reasonably reliable up and running within a week. Then we pulled a validation set, and that's how we were actually looking to compare things. And then we actually did a robustness test where so the validation set was the week after all of the training data ended, or a full week later. But the validation set was actually in September. So we wanted to go all the way to the shoulder season to some pretty significantly different data. We were having highs in the mid-20s in July. We were having highs in the teens in September. So just to see how valid and how, if you had data that was entirely out of the training distribution, how well you could adjust. So as you can see, you can get a fairly complicated equation in SRA. Nothing particularly surprising. It's a combination of wet and dry bulb temperatures and humidity in a variety of different forms. So it's a complicated model. Does it make physical sense? It makes sense that those variables would be part of it, but it doesn't necessarily follow intuitively. Your SRB is basically looking very, very simply at your wet bulb temperature, your humidity, and your dry bulb temperature, and then our SRC was a very, very simple model. So just really trying to figure out how simple we could make it, how little computational power we could have. Nice thing, we don't have neural nets. If you wanted to put this onto an edge processing device like an FGPA card, you don't even need an FGPA. You could do it on any standard PLC because this is all very simple PLC logic that you can program. And here's our model validation. So the SRA was actually the most accurate, and we kept that in the paper. What we were really interested in is how easy or how well the much simpler models could actually fit. And if you actually look at it, our actual versus prediction, and this is on the validation set, not on the training set. So this is new data that the models hadn't seen, but it was from the same season. And you can see that the SRB is performing very well. SRC is not performing quite as well. We said it's only 3 days of data. To be honest, I think for 3 days of data, we're still doing reasonably well, right? If you look at the scatter plots, if we were to plot residuals, you can tell obviously there's some nonlinearity that we haven't picked up, right? But they're still reasonably good. In terms of the area that we're looking at, we were reasonably happy with how well these simple predictions were actually coming. And again, this is on the validation set. And then if you look over at comparing the evaluation metrics, I'm much more interested in the RMSE. than the R-squared. I find R-squared is sometimes a little bit of a funny thing for things that aren't necessarily linear relationships, but yeah, they're decent values. But your RMSE, we're looking at about 232 watts to 280 watts. When we're talking kilowatts, when you're talking 4,500 is the order of magnitude, this is about a 5% error, which is, again, not bad for startup. With a couple of months, that obviously decreases, but this is also a very simple model. And we're just trying to look and see how well we could actually bring things back down in terms of having long-term performance on this model. So when we modeled it on the validation set, you can see that we actually got reasonable models. We are slightly outperforming, like SRA is outperforming everything except for XGBoost, or XGBoost. But if you actually look on the out-of-distribution tests, and this is where we thought it was actually really interesting, our symbolic regression models suddenly outperform everything, right? So you have these much more powerful models, like the XGBoost is arguably a lot more powerful than a very simple equation. But we're significantly outperforming it on the out-of-data test. And we're still having reasonably, it's not great error, but reasonably good predictions when we're actually looking in the September data set. So we're looking at a completely different season, and we're still out-competing everything else. So we're now off maybe with 10% error on our RMSE, right? So it's nice to actually get a sense. We're really happy, We're really happy with how the results have turned out. This is kind of our first exploration into the symbolic regression. But it's nice to see how well we can actually come up. So when we're seeing that as our linear regression and our XGBoost are dropping, our symbolic regression is actually able to hold on to it. And that's the beauty of these physics-based models. So just to quickly summarize, our symbolic regression basically gives us a robust approach where we can actually do load forecasting. This is just one part of a bigger project where we have an emulator for the chiller, the cooling tower, the cooling plant that we're in the process of deploying across a series of hospitals across Canada, so we can actually test more generalizability. And this is very easy to be able to control locally on a controller. One of the big goals was to simplify this as much as possible to actually allow field implementation. Future direction, obviously, first one is to extend to a variety of buildings. We do have a building campus with a lot of different mixed-use buildings that we can actually test it on. We can look at different system configurations to see how well this works. We can look at different hospitals and different climate zones and see how similar the formats of the equations are. And we can also look at how we can further optimize some of these approaches and then maybe look at retraining with broader data sets. So how can we start to bring in continuous learning? And can we make it so that these models can then retrain themselves as more data becomes available? But this really, like I said, is a cold start problem. And for 3 days out of season, I'll take the MAPE as high as 40% on some of the peak days. Got one reference, and just to acknowledge our sponsors, we're sponsored by the National Science and Engineering Research Council, and HH English, which is an engineering firm that does a lot of hospitals design on a collaborative research grant, and of course our university has been an incredible support for us as well. So, questions?